All right, we are at topic 15, electric forces and fields. And I'm not starting with a share. We're gonna try a little experiment. Well, let me do this first, see if it works. Comb my hair. Hopefully it's dry enough, and we'll see what happens to all these papers here. Oh, it picked up some of them. You can see it, there's some static buildup that occurred, and we're gonna see, just like they do in the notes. Let's share the screen. It starts off with this. It starts off with a rod that has, I didn't pick up as many pieces of paper as this rod did, but there was, it did pick up some pieces of paper because there was a transfer of electrons that cause an imbalance that causes these bits of paper to be picked up, and so we're talking about electric forces. So there's enough electric force to attract, to lift up these bits of paper, and you can see you see this when a child with long hair slides down a slide. Often they have long hair. They static buildup of sliding down the slide will cause their hair to lift up to the plastic. And here they're showing you examples. A negatively charged rubber rod suspended by a string is attracted to a positively charged glass rod. So there's a force, there's an attractive force between the negative and the positive. And then it shows a negatively charged rubber rod is repelled by another negatively charged rubber rod. So just from this one slide, we learned that opposite charges attract and like charges repel. You can see the negative and the negative, they repel each other. If it would have been a positive and a positive, they would have repelled each other. And we're going to see that. Okay, there's the text: like charges repel, unlike charges attract. Each negatively charged electron transferred from the rod to the silk leaves an equal positive charge on the rod. So we're not creating charge. There's always, if you transfer charge from one to the other, there's an equal amount of charges taken off as there are that are put on the opposite item. Charge is quantized. I am losing my notes. This is a picture of Robert Millikan. He's in 1909. Robert Millikan discovered that if an object is charged, its charge is always a multiple of a fundamental charge, E. Charge is quantized, and E is equal to 1.60219 times 10 to the minus 19 coulombs. We will deal with coulombs, but most of the time we're going to deal with nanocoulombs, microcoulombs, multiples of coulombs. But if whatever it is, if it's 300 nanocoulombs, then it's 300 times 10 to the minus 9, 300 times 10 to the minus 9 coulombs. Okay, insulators and conductors. Insulators, things like glass. There's not very many free electrons, so they don't transfer charge very well. Or you have the wire on the other, where it does have an excess of electrons. I mean, it's neutral when it first when you first have it, but then when you start applying voltage, you can get the electrons to move. It's a conductor. And what they're showing here, these are insulators. This is actually, these are semiconductors. This is they can be used to change the conductivity of a particular material. Here we have, these are semiconductors. It's a third class of materials. Their electrical properties are somewhere between those of insulators and those of conductors. Silicon and germanium, shown in the photos, are well-known semiconductors that are widely used in the fabrication of a variety of electronic devices. Okay, charging by conduction. You can, if you were to count the number of charges on the blue ball, you would see that there's an equal amount of positive charges and an equal amount of negative charges. Now, before contact, the negative rod repels the sphere's electrons, inducing a local positive charge. So just bringing this rod that's negatively charged near, you can see that you have the pluses on this side and the minuses on this side. What has happened? Well, remember, opposite charges attract, so the positive charges are attracted to these negative charges on the rod, and they also repel these negative charges, so they go to the other side of the ball. When you touch it, after contact, the electrons from the rod flow onto the sphere, neutralizing the local positive charges. Now, when the rod is removed, the negative charge remains on the sphere. Okay, so you've just charged the ball by conduction, by actually making contact, allowing the charges to go onto the ball. Okay, the neutral sphere has equal numbers of positive and negative charges. Electrons redistribute when the charge rod is brought close. And, oh, I'm sorry, this is charged by induction. Now, the last one was charged by conduction. This is charged by induction, meaning that we're not really going to touch the charge. So there's an equal number of positives and negatives. We bring a negatively charged rod nearby, and you can see the same thing happens. The positives are attracted to the negative rod, and the negative particles are pushed away. Then we bring a wire. Some electrons leave the grounded sphere through the ground wire. We touch this to what is called electrical ground, and some of the charges leave. Now, we've never made contact with this rod, and once we remove the path to ground, the excess positive charge is non-uniformly distributed to the in the sphere. You can count, if you count them up, there still are more positive charges than negative charges. And even if we remove the negatively charged rod, the remaining electrons redistribute uniformly, and there's a net uniform distribution of positive charge on the sphere's surface. Okay, you ever rub a balloon on your head and put it onto a wall? This is what's taking place. You charge a balloon by rubbing it on your head. This is typically in very dry climates. If it's humid, it doesn't work as well. The positively charged balloon induces a migration of negative charges to the wall surface. Now, the wall is still neutral, but you can see that it attracts these negative charges on one side, and the positive charges are pushed away. So you have these induced charges, and the electrostatic force between the attractive force between the positive and the negatives hold the charged balloon to the wall. And that's it for section 15.1. We're going to talk about Coulomb's law in the next section.